Okay, so we are still talking about extreme values of functions. So we already reached now chapter 4. Okay, last time I already explained why we are actually interested in this problem. So there are many problems arising from application where we are interested in maximum and minimum values of given functions. I told you some simple examples last time, like if you want to produce a cane or some box and you are interested in minimizing the production cost, then you are essentially led to a extreme value problem. So you essentially have a function and you want to search the minimum of a given function. And you have in your textbook a couple of other examples explaining why this problem is important. Now, last time I already defined absolute extreme values. And also local extreme values. And just to stress this point once more, so last time I showed you an example that, of course, the definition here is straightforward, but sometimes you have to be a little bit careful. So last time we looked at this example here. Okay, where x is between -1 and 4. So if you plot the graph of this function, you can find the graph in your textbook. Then the function looks roughly like this here. Okay, but those points here are included because we are looking at, so the scale here is not very good. This here should actually be -1. Then this here should be 1. Then we have somewhere here 2. And we have here 3. And we have here 4. Okay, so the only important thing to stress is, of course, you see the local extrema. So for instance, you see that this here will be a local maximum. You see that this here is a local minimum, even an absolute minimum. You see that the absolute maximum is achieved here at the boundary point, x is equal to -1. The only important thing to stress is, if you look carefully at the definition in our textbook, this here, the point x is equal to 4 is nothing. So this is not a local extrema, okay? Because you easily, it depends on the definition actually, whether you accept this here as a local extrema or not. It's obviously not a It's obviously not the absolute maximum, okay? But you could say, okay, you could use a different definition for local maximum and say, okay, this is for you also a local maximum, okay? But actually, some textbooks include this in the list of local maxima, but we are going to exclude this case here. So this is for us nothing, okay? So this is important to stress. It's just a definition. Now. We know by looking at several examples, for instance, if you look at the example f of x is equal to sine of x. Okay, so this function has many local maxima and local minima, which are indeed all local, all absolute maxima and absolute minima. Now, if you look at this function here, f of x is equal to x squared. Okay, we know just by plotting the graph. Okay, there is only local minima, which is actually also the absolute minima. And if you look at this function here, then this function, if you plot the graph, this function has nothing. So quite a lot can happen. Now, so it can happen that the function, for instance, has no local extrema, or only one, which is a minimum, or many. So the first thing we need is actually a theorem which tells us, gives us some condition under which we can easily see that the function has extreme values. And this theorem is called extreme value theorem. So you'll find in your textbook a theorem which states the following. So this is called extreme value theorem. Okay, so if you have a function f continuous on a closed interval AB, then f has both absolute maximum and absolute minimum. Okay, so I guess this is a result you easily believe. If you look at some examples, if you check some examples, you see that it seems that this is indeed true. So we are talking here about you should notice this. We are talking here about absolute extrema. Okay, so for instance, if this is our interval AB and we look at the function. Okay, so for instance, this one, where those 2 points here included. Okay, so you see that, okay, so you have here the absolute maximum roughly at this point here, this point, and you have the absolute minimum at the point B. So for this, the function is continuous because I plotted the graph just without lifting the pencil, okay, just in one stroke. And you see that, okay, this function satisfies the assumption being continuous, and indeed this function has a absolute maximum and the absolute minimum. If you look at some different examples, or if you check a couple of examples, you will see that this result is indeed true. So for instance, if the function looks like, okay, something like this here, okay, so here you see, okay, this here will be the absolute maximum, and this here will be the absolute minimum. C1 will be the absolute maximum, C2 the absolute minimum. And you can check more functions, and you will see, indeed, this is always true. So this result tells you, it's a so-called existence result. It tells you, okay, there exists an absolute maximum and absolute minimum. It doesn't tell you how to find it. And it doesn't tell you either whether the absolute maximum and absolute minimum is unique or not. Okay. This result here looks, I guess everyone is going to believe this, looks very easy. But we cannot prove this because this is essentially a language problem, because we haven't developed the basic language in order to prove something like this here. Okay, so the proof is not so easy of such a result. Also, it might look completely obvious. Okay, and you don't have to, you shouldn't try it. Okay, because essentially what you miss is the right language in order to prove something like this, which is normally taught in more advanced classes of mathematics. So we are going to accept this theorem. So for us, we know, okay, whenever we have a continuous function on a closed interval AB, we know that this function must have an absolute maximum and an absolute minimum. And what I want to stress, and what is stressed in the in our textbook as well, is that the assumptions here are all necessary. Okay, so you cannot drop them. So for instance, if you consider the function, if the function is continuous, not on a closed interval, but for instance, half open AB, okay, this result is not necessarily true. Okay, so for instance, you have easy examples, easy counterexamples. For instance, if you if you look at a function which has a vertical asymptote at x is equal to b, so our function looks like this here. Okay, so this function would be continuous on the half-open interval from a to b. Okay, so the only difference to this situation is that you have here the half-open interval. Okay, but still the conclusion is not true, because you see this function has it indeed has an absolute minimum, but it doesn't have an absolute maximum. And if another situation would be that the function is not continuous, but this situation is even more easier because the function, for instance, might jump, and then it might be possible that you do not have, for instance, the absolute minimum. So also here it's easy to find the counterexample. Okay, so for instance, if the function looks like, okay, so we go something like this here, and then at some point c, the function jumps, so it's not continuous. Okay, so you see that this function does not have an absolute minimum, but but the function has an absolute maximum, namely here. It depends here, so maybe here. Okay, so you see that actually you need both of the conditions. You need continuous, and you need that the interval is closed. Okay, which means here that both boundary points are included. Otherwise, the result is not correct. Okay, so any questions to this? Our first aim is not to find absolute extreme values, but local extreme values. Now, for local extreme values, you find an important result in our textbook, which is quite obvious. So, if you have a function, okay, you know already from high school, okay, if you want to find the local extremas, okay, if you have a local extrema, the tangent at this value where the local extreme value occurs, okay, has to be horizontal, which means that the derivative has to be equal to 0. Okay, so this is something which you know already from high school. So this is another theorem which is called in the textbook Fermat's theorem. You might have heard of this mathematician. This is a famous French mathematician, because there is a famous problem which is called Fermat's last problem, which was solved now already 10 years ago, or more than 10 years ago. So maybe you've heard about this. It's the same. This is the same guy. I'm not sure why the textbook calls this theorem Fermat's theorem. I doubt that this theorem is going back to Fermat. And actually, this textbook is the first book where I saw that this theorem is called Fermat's theorem. Now, this is a very easy result, so I guess many other mathematicians have discovered it as well. So, actually, you can forget about this name here, but it is referred to in the sequel always as Fermat's theorem. Now, this theorem is what I just said before. So, assume that f is differentiable at C, and f has a local extreme value at C, then the derivative of f of c must be equal to 0. Of course, for this, you need some assumptions. Of course, you need that f is differentiable, because otherwise the tangent at the point c does not exist. Okay, so you need, of course, that f is differentiable, and we assume that we have an extreme value. And you see from the graph already that okay, in this case, the tangent at c must be equal to 0. Now, if we do not argue with the graph, you find a proof in our textbook. So maybe let's just quickly look at the proof. So the proof is not very complicated. if you look at the graph, okay, everything is clear, okay, but arguing without the graph, you just have to write more, okay. So we assume, for instance, we proved the theorem for the case where f is a local minimum or local maximum. It doesn't matter. So let's maybe choose the case where f has a local minimum at C. Okay. The proof then for the case where f is a local maximum will be just the same. Now we can choose. This means we can choose h small enough such that f of x plus h, f of c plus h is larger or equal than f of c. Okay, so because this extreme value is a local minimum, okay, so we know that there exists around C a small interval, and for all x values in this small interval, okay, you have this inequality. So in particular, you can choose a small enough h such that this inequality will hold. And now you just divide into two cases. So you first consider the case where h is larger than 0. Okay, so in this case, get that f of c plus h minus f of c over h. The only reason why I need this assumption is because if h is smaller than 0, then this will be smaller or equal than 0. Okay, so since h is larger than 0, if I divide by h, I get larger or equal than 0 for the inequality. Now I use the assumption that f is differentiable at c. So I know that if I take the limit here, as h tends to 0, this limit will exist, and is equal to the derivative. So the derivative at c will be equal to the limit as h tends to 0 of f of c plus h minus f of c over h. But actually, if I want to use this inequality, okay, I have to look at the limit from the right. Okay, f of c plus h minus f of c over h. Okay, and now because if the h is larger than 0, I'm in the first case, so this will be larger or equal than 0 here. And if I take the limit on both sides, we know we have proved that the relation will also hold in the limit, so this will be larger or equal than 0. So I have already proved that the derivative of f at 0 is larger or equal than 0. And now if I look at the second case, where I consider h which are smaller than 0, then I just get the same result, but the inequalities are all in the other direction. So then I get that the derivative of f at c is smaller or equal than 0. But combining those two here, I see that the derivative of f at c is equal to 0. Okay, this is what I wanted to prove. Of course, the proof is rather simple because if you look at the graph, okay, everything. If you look at the graph of the function, everything is clear. Okay. Any questions to this? Maybe you should be careful, okay, if you have an inequality and you divide by something, okay, because also in the assignments I saw that some students use something like this in order to solve the example where you have the sine 2 to the n x minus 2 to the n sine of x over x square. So some students try to use the squeezing theorem, but you have to be very careful if you have some estimates, okay. You have to be careful if you multiply with something which is negative, the inequalities will all change. The direction of the inequalities will all change. Okay, this is an easy situation here. So we know that if a function is differentiable, and has a local extrema at some point, then the derivative at this point must be equal to 0. This was just a case where we have a local minimum. Okay, I just said that for a local maximum, you use the same proof, but it's even easier to replace the original function by minus the function, and then say, okay, you can use the same way of reasoning. So actually, you do not have to do things twice. Now, if you look at some examples, and you know this already from high school, the inverse of the theorem is not necessarily true. Okay, so whenever you find a point where the derivative is equal to 0 at this point, it is not necessarily true that the function has a local extrema at this point. We already saw one example. So if you have f of x is equal to x to the cube, so if you take the derivative and equate it to 0, you see that x is equal to 0 is the only point where the derivative is equal to 0, but the function does not have has not a local extrema at x is equal to 0. Okay, so you see the inverse of what the textbook calls Fermat's theorem is not true. From this example, you also it's also important because in high school what you normally do is, okay, you take a function, you take the derivative, you find all zeros of the derivative, all roots of the derivative, and these are essentially the points where you might have local extremas. You see that if you look at the assumptions in Fermat's theorem, there is another assumption which tells you the function must be differentiable. Okay, so using such an approach, you might lose. So if you just look at the derivative, equate it to 0, find the roots, and then check at those roots whether you have local extremas, you might not find all the local extremas. An easy example is the function f of x is equal to absolute value of x, where the derivative for certain x exists. So the derivative is you can call it the sine of x. So 1 if x is if x is larger than 0 and -1 if x is smaller than 0. Okay, so you see that the derivative does not have any zeros. Okay, but the original function has still a minimum, local minimum at 0. Okay, so it's not just enough to take the derivative of a given function, okay, and compute the roots of the derivative and check whether at the roots you have local extremas. You also have to consider the points where the function is not differentiable. Okay, so all the local extremas, you can find them as all local extremas are a subset of the set of all roots of the first derivative plus all points where the function is not differentiable. So, and because this set is important, because that's essentially the set where we are going to check whether the function has in this set local extremas, because that's enough. This set of numbers, such numbers are called critical numbers. Okay, so we have the following definition. Okay, so C is called a critical number of f if either the derivative of f at C is equal to 0 or the derivative of f of f at C does not exist. Okay, and if f has has a local extrema, okay, at C, then C must be a critical number. That's the important thing about the critical numbers. So you can now reformulate Fermat's theorem. So you can call this another version of Fermat's theorem. If F has a local extrema at C, then C is a critical number of F. Okay, so if you want to find all the local extreme values, all the local extremas, what you do is you first find all the critical numbers, and then this restricts your set of all possibilities, okay, to a much, much smaller set for most of the functions, okay, and then you just have to search in this set, in the set of critical numbers, whether the numbers are local extremas. But we know that some of them might not be a local extrema, okay, so the real set of local extremas might be really a subset of the set of critical points. Okay, so any questions to this? Now, because you know that not next week, but in 2 weeks we have our midterm. In my midterm, of course, it's important that you know how to do computations, but most of the questions will check whether you understand concepts. This is more important for me, whether you understand basic concepts. It's not so important to do computations, okay? So you will not find that many examples in my midterm, so maybe 8 or even less, or 8 to 10. It depends. Every year is different. But you have but most of the questions will ask your basic understanding of the material. Now, what I like to do every year is I like to have questions where you have a statement, and the statement might be right, or it might be wrong, or it might be right in some cases, wrong in other cases. So you have 3 possibilities, and you should decide which one is the correct one, and you have to argue why. Okay. Now, I show you an example. I know from experience that these are normally the examples where students have most problems. So there will also be some easy examples. There will not be very, very easy examples. Okay, I'm not going to ask you what is my name. Okay, it seems to happen in high school here. Okay, so so you will also have some easy examples. Okay, but the main thing about my examples will be asking whether you understand the concepts. Now, for instance, an easy example might look as follows, as the following one. Okay, so for instance, assume that f is continuous on some interval AB and increasing. On AB. Then I might give you a couple of statements, like first, f has global extremas. This is the first one. Second, of course, on AB. The second is f has local extrema on AB. And the third, f has no critical points okay, for every statement you have 3 possibilities. Always true, which means for all f true. For all f satisfying this assumption. Or never true, which means, okay, for no f satisfying this assumption here, the statement holds. Or true in some cases, true in others. Okay, you have then to decide for every statement, okay, what is the right answer, and you have to argue, okay, not just to give the answer, so you have to argue why. Okay. So for instance, because you have 3 possibilities, if the answer is, or it might be also 2 possibilities, it depends on the questions. Sometimes it's only true, wrong. But here for such an example, it's normally you get 3 possibilities. Now, if it is always true, then you have to either prove it or refer to some theorem in our textbook which proves the result. If it is always wrong, also either prove it or argue by using a theorem. If it is true in some cases, wrong in other cases, you just have to demonstrate, to find examples, to find one function where the statement is true and another function where the statement is false. It's wrong. Okay, so what is the answer here? What is the answer of the first statement? Okay, so if right, the answer is true, and what you have to write in the midterm is because of the extreme value theorem. Okay. Actually, the extreme value theorem. Okay, this is terminology, so you have to know this. You should know this word. Okay. Now, how about the second? Wrong. How do you argue? Okay, so there is no theorem which tells you this is wrong here, so you have to argue more. But this is here pretty easy because it's because of the definition. Because if there would be a local extrema, okay, of course the local extrema must be inside AB, okay. But if you are inside AB, okay, this means for every point inside AB you can find a small interval which is around this point and is still in AB. But there you have the condition that if x is smaller than x2, f of x1, if x1 is smaller than x2, then f of x1 is smaller than f of x2. So the definition cannot hold. Okay, so you do not have to be that careful, but you do not have to write an essay. Okay, but try to be careful in how you argue. Now, how about the last question? Wrong? True, you think it's true, always true. True here means always true for every f. Okay, so here you see that the answer is true in some cases, wrong in others. So in particular, the second does not imply the third. Okay, so it's because in the second you have discovered there are certainly no local extremas. So it's not true that this implies that there are no critical points because. And here, if you have something like this, you just have to give 2 examples, and I will be satisfied. So, for instance, it's enough to plot a graph. It's also okay if you give a function directly. So, for instance, this function, okay, does not have a critical value, but for instance, this function, okay, this function has a critical value. This function is still increasing, but at this point, the function is not differentiable, and the critical points are defined as the points where either the derivative is equal to 0 or the function is not differentiable in the point. So here in this point, here this is a critical point. Okay, and this is the way how you have to argue if you have an example like this. Okay, so any questions to this? Okay, so let's maybe look at an example where we compute critical values. So for instance, if we have this example here, then we see, okay, the derivative okay, so the derivative is never equal to 0, but the derivative does not exist at x is equal to 0. So 0 is the only critical value. But of course, from the graph, you see that at 0 you have nothing. You do not have a local extreme value. Now, if we look at this at a different example, for instance, this here. Okay, so and you are asked to find, okay, what are the critical values? Okay, so you see already that the function, that one critical value is 0. Okay, so how do you argue? So the function is not differentiable at 0. Would it, if it would be differentiable at 0, okay, then you would add, then you can add plus x squared, and the resulting function would be differentiable at 0 as well. But this is the absolute value of x, and we have proved that this function is not differentiable at 0. So you see immediately that 0 is a critical, not value, point. Sorry. Okay, in order to find the other critical points, you have to compute the derivative. So the derivative of this function, of course, you split your considerations into two cases. X is larger than 0, where you have 1 minus 2x, and x is smaller than 0, where you have minus 1 minus 2x. And you have to equate this to 0. So you see that if you equate this to 0, then you get two zeros, namely x is equal to 1/2 and x is equal to minus 1/2. So you see the set of critical points here is 1/2 minus 1/2 and 0, and that's then this is the set of the possible points where you might have a local extrema. Okay, now for such a function, actually it's also very easy to figure out, okay, whether where is the extreme value if you look at absolute extreme values. And this is a method which the textbook calls the closed interval method. So for instance, we assume that, let's say we consider this function on the closed interval from -1 to 1, and we are asked to find, we know that this function here, because this function is continuous, okay, on this interval, we know that there must be an absolute maximum and absolute minimum, okay, by the extreme value theorem. Now, this closed interval method works as follows. Since you know there must be an absolute extreme value, the absolute extreme values must exist. So this means you have just to check the critical points and the two boundary points, and you are done. And from all those values, you search the largest and the smallest. The largest will be the absolute maximum value, and the smallest will be the absolute minimum value. Okay. So the basis for this method is the extreme value theorem. Okay, because we know there exist absolute extreme values. So that's the reason why we can proceed like this. So here you proceed in 3 steps. Step 1 is compute all critical points. And evaluate f on the critical points. Then the second step is compute f of 1 and f of -1, f of a and f of b. So our task is to find the absolute extreme values of the function f on AB. So compute the values on the two boundaries and then choose the largest. And smallest value from 2 and 3. Okay, so here in this case, A is equal to -1, B is equal to 1, and we should find the absolute extreme values of this function on this interval. So the only points we have to check here are the two boundary points and all the critical points which are here 0, 1/2, and -1/2. So here in this case, we compute f of 1, which is equal to 0. We compute f of -1, which is equal to 0. We compute f of 0, which is equal to 0. We compute f of 1/2, which is 1/2 minus 1/4, so -1. So 1/2, 1/4, and f of -1/2, which is 1/2 minus 1/4, just the same, so 1/4. So you see that this here, 0 is the absolute minimum value, and 1/4 is the absolute maximum value. And you have here 3 points where the absolute minimum value is achieved, and 2 points where the absolute maximum value is achieved. So once more, the basis for this method here, for the so-called closed interval method, is the extreme values theorem, because we know that a continuous function on a closed interval AB must have an absolute maximum and absolute minimum. And we know that if the absolute maximum and absolute minimum is not one of the boundary points, then it's inside, and then it's also a local extrema. But local extrema must be contained in the set of critical points. Okay, so for continuous functions on a closed interval, it's finding absolute extreme values is very, very easy. You find many examples in our textbook. So, for instance, if you have this example here, minus ln of x, and x is in this interval here. So you see that the function is continuous on this interval. The interval is closed, so you can use the closed interval method in order to find the absolute extreme values. So what we have to do is we have to find the derivative, which exists everywhere. So we have 1 minus 3 over x. We have to equate it to 0. So we see that x is equal to 3 is the only critical number Okay, so we have just to check 3 function values, namely f of 1, which is 1, then f of 3, and f of 4. And if you do the computations here, then f of 3 is minus 0.296, and f of 4 is minus 0.16. Okay, so you see that because this is the largest value, so this must be the absolute maximum, and this here is the smallest value, so this must be the absolute minimum. This method, you can just use it in order to find absolute extreme values. It doesn't tell you anything about whether, if you have more critical numbers, it doesn't tell you anything about whether at other critical numbers you might have local extreme values. Okay, so any questions to this? I don't think it's necessary to do more example here. This method should be easy enough to apply. So we know now how to find local extreme values, global absolute extreme values. We do not know yet how to figure out whether which of the critical points are local extreme values. We will postpone this problem to section 4.3, And before we go on, we have to discuss a very important tool, which will be one of the main tools in the sequel, and this tool is called the Okay, so in this lecture we will only learn, or in this course we will only learn a couple of theorems which are very, very important. This is one of them, so we will learn maybe 3 or 4 theorems which are really very important. This you can consider this as the first one. Now, before we are able to state and prove the mean value theorem, we have to look at another theorem. Which is due to a French mathematician called Rolle. Does it have an E or not? Okay, so it's Rolle theorem. Now, we have given a function, assume that f satisfies 3 conditions. So the function is given on a closed interval AB. The function satisfies first f is continuous on the closed interval AB. Second, f is differentiable on the half open interval, on the open interval AB. And the third condition, f of A is equal to f of B. Okay, now, if you think about the geometric situation, the function f is a continuous function on AB, and at A, the value is just the same at B. So just from this, you would already guess that there must be some value inside the interval AB where the derivative is equal to 0, or in other words, where you have a horizontal tangent. And this is exactly what Rolle's theorem tells you. So there exists C in the open interval AB such that the derivative of f at C is equal to 0. Okay, so actually this result, if you think about the geometric situation, is pretty obvious. You have the function f, and the function starts at the same value. At A, the value is just the same as at B. Okay, the function is continuous. So obviously, for instance, the function can look like this here, but then you have a point where the tangent is horizontal, or the function can look like this here, but then you have even 2 points. Okay, so just from the geometric situation, this result should be obvious. And this result will be our first result towards the mean. We will use this in order to prove the mean value theorem. That's essentially why we consider it. Okay, now how to prove this result? Okay, so you look at 3 cases. Case 1. Okay, case 1, you assume that the function is constant. Now this case is the most easiest case, because in this case the derivative will be equal to 0. Okay, so the theorem is okay in this case because you can choose any C between A and B, and the derivative will be equal to 0. So this is the first case. The function is constant. Now in the second case, okay, the function is not constant. Okay, so this, for instance, means there exists an x, or call it, let's say, a C, in the interval AB, or maybe let's say with f of C will be larger than f of A. Okay, because the value at A and B of the function is the same. So if the function is not constant, there exists either a C, okay, where f of C is larger than f of A, or there exists a C where f of C is smaller than f of A. Okay. Now it is clear that because f of A is equal to f of B, so C is even in the open interval AB. Okay. But we know that now you can choose for C actually the maximum. Okay, so you choose the largest value on AB, and the largest value must be larger than f of A. Now, since you know that C is in AB, okay, this means that the function has a local extrema at C. But the function is differentiable everywhere. So from this, now we can use Fermat's theorem, so we know that the derivative of f at C must be equal to 0. And this is our C here. Okay. So maybe once more. First of all, if the function is not constant, okay, we know that there exists a C. But here for this step, actually, I need the extreme value theorem. So I use the extreme value theorem here. I know that the function must have an absolute maximum. Okay. Now we assume, since the function is not constant, if you have something like this here, okay, the absolute maximum must be inside the interval. Okay. And then you just observe that because the C is inside the interval, the absolute maximum is also a local maximum. And the function is differentiable everywhere, so the derivative is equal to 0. And you use the same way of reasoning if in the third case where you have a C in the interval AB where f of C is smaller than f of A. Then again, if this C is not the absolute minimum, okay, you choose the absolute minimum. The absolute minimum must be inside the interval. The function. So this means that the absolute minimum is not only an absolute minimum but also a local extreme value, and then since the function is everywhere differentiable, the derivative must be equal to 0. Okay, so you see that in order to prove this theorem, you already need the extreme value theorem, and you need Fermat's theorem. Fermat's theorem we have proved, but the extreme value theorem we have not proved. So actually, it wouldn't be that easy for us to prove this theorem if we wouldn't have the extreme value theorem. Now, this theorem here, Rolle's theorem, I told you one reason why we are going to look at it is because we want to use it in order to prove the mean value theorem. But this theorem is also important. Is also important on its own. You find the following example in our textbook, which shows applications of Rolle's theorem. Namely, if you look at the following equation, and the task is to prove, okay, that this equation only has one root. Okay, so prove that f of x has exactly one root. Exactly one root. Okay, so how do you do this? Now, such proofs you do in two steps. First, you prove that you have one root, at least one, and then you prove it's the only one. Okay, so actually you prove first that you have at least one root, and then you prove you have at most one root, and then you get that you have exactly one root. Now, for the first step, okay, we observe that f of 0 is equal to -1. Okay, we observe that f of 1 is equal to 1. Okay, so and we observe that the function is continuous on the closed interval 0, 1. Okay, so you can use the intermediate value theorem. Okay, to argue there must exist a C in the open interval 0 and 1 such that f of C is equal to 0. This is not this theorem here, okay? This is the intermediate value theorem which I use here because the function is continuous, starts at -1, will go on to 1, so it has to take on every value in between. In particular, 0 must be taken on by some value in between. So this proves, okay, that you have at least one root. Now, in order to prove that there is only one root, you use this result here. So kind of you can say this proves here existence. Now we have to prove that the root we just found is unique. Okay, and for this it's very easy to argue. You assume you use proof by contradiction, so you assume there are two roots. Okay, so assume that f of c1 is equal to 0 and f of c2 is equal to 0 as well. Of course, without loss of generality, you can assume that c1 is smaller than c2. Okay, otherwise you just change the name. Now you check. Okay, the function f is a polynomial, so the function is certainly continuous on the closed interval c1, c2. The function is differentiable on the open interval c1, c2. Okay, and you see that f of c1 is equal to f of c2. So all the assumptions of Rolle's theorem are satisfied. So Rolle's theorem tells you, okay, there exists some number c such that the derivative at this number is equal to 0. So this is by Rolle's theorem. Okay, but if you now look at the derivative of this function here, okay, this derivative of this function cannot be equal to 0. So it's larger or equal than 1. Okay, so you have a contradiction. Or in other words, it was wrong to assume that we have two zeros. Okay, so such examples, you prove them in two steps. The first step will use the intermediate value theorem, okay, to check whether there is a root. So this is existence. You prove existence here, and then you use Rolle's theorem in order to prove that the root is unique. You see, actually, the same reason holds here. If you replace here the constant, the coefficient by a, where a is larger than 0. Okay, so for instance, if you look at the derivative, you see you get here an a. Okay, so the derivative cannot be equal to 0 for this function here. So this already tells you there's at most 1, okay? And there will be 1 because if x is very small, this will certainly be negative, and if x is very large, this will certainly be positive, because if x tends to infinity, this tends to plus infinity, and if x tends to minus infinity, it will tend to minus infinity. So you will certainly find a small enough x and a large enough a small enough x and a large enough x such that at a very small x, the function is negative, and at a very large x, the function is positive. And because it's a polynomial, so continuous, so you can use the intermediate value theorem to show that there is a root in between. So this even holds for this general polynomial where a is larger than 0. Okay, so any questions to this? I actually had also another exercise in last year's midterm. You remember we once discussed an exercise which I told you this was one of the exercises last year in the midterm, which was roughly as follows. So you have here Taiwan, you have here Austria. Now, normally in summer, I fly from Taipei to Vienna. Okay, and you assume that on Monday I fly from Taipei to Vienna. The airplane will start in Taipei at 9 o'clock in the morning, and the flight roughly takes 12 hours to go there. And then 1 week later on Monday, I come back to Taipei. Okay, so you remember this example. We discussed this before. So before I told you to argue by using the mean value at the intermediate value theorem that there is a point T, okay, where on the way there and on the way back here, you are at the same place. Now, actually, this exercise had the A part and the B part. The B part was use Rolle's theorem to prove that this point is unique, and the question and there was also a question which asks you, okay, which assumptions do you need for this result to hold? Okay, so I'm not going to repeat the original question, so I just tell you the new questions. So use or argue with Rolle's theorem. Use Rolle's theorem to show that the time point is unique. Which assumptions? Do you need for this? Actually, the question should be different. It should be, okay, give assumptions under which you can argue by using Rolle's theorem such that the point is unique, the time point is unique. Now, of course, you need some assumptions for this, because it should not be that the airplane is like flying back and then going again into the direction of Austria. So the distance, if you fly from Taipei to Vienna, okay, the distance to Taipei, okay, should get larger and larger, okay, should not decrease. So you remember that we defined two functions in order to answer that such a time point exists. So the first function, so here you have the time. So the first function gives you the distance. Now you're flying from Taipei to Vienna, so the distance to Taipei. Okay, so at the beginning the distance is 0, and then at the end the distance will be the distance between Vienna and Taipei. And on the way back here, so this is the first function. Okay, and then on the way back you do the same, but you consider the distance to Taipei. So at the beginning, okay, the distance will be the distance between Taipei and Vienna, and then it will decrease to 0. Okay, so this is the function g of x. Now you see already from the picture, you see, okay, there is one such a time point where the distance to Taipei and the distance from Taipei is the same. Or in other words, at this time point, you have passed the same place. Okay, and you also see from the graph, okay, actually this point will be unique here. Okay, what you have to assume is that g is decreasing and f is increasing. Okay, now in order that g is decreasing, okay, you know already from high school that the derivative must be smaller than 0. This is something we are going to prove rigorously in the next section. And for f, you assume that the derivative is larger than 0. Okay, and then you just use the same reasoning. So if you assume that you have two points. So we consider again the function, call it maybe f of x, which is minus g of x. Okay, so assume that there are 2 time points. Actually, the x should be t, would be maybe better, such that f of t1 is equal to f of t2. But if you look at the derivative, okay, then you see 1 is positive, this one is negative, so it's larger than 0. So this cannot be true. Okay, because from Rolle's theorem you would get that okay, there must be a point between t1 and t2 such that the derivative is equal to 0. But this cannot happen under these assumptions here. So these are the assumptions you need. Okay, so this function must be strictly increasing. This must be strictly decreasing. So for instance, the plane should not stop somewhere in between. Okay, so if you have no transit, nowhere, then you can assume okay, these conditions are satisfied. Okay, such an example, okay, has maybe not too much. So such an example is not, you do not have to compute something, okay. So it's not, the essential thing is not on the computation part. The essential thing is that you understand concepts, okay. That's why I like to choose such examples in order to check whether students have a basic understanding of the main concepts. Okay, any questions to this? So for the midterm, you are invited to argue carefully. You also should, if you have such an example, you should memorize, okay, what are the assumptions for Rolle's theorem. Okay, you have to state clearly, okay, why are the assumptions satisfied? Or in this case, you have to say, okay, what this second question, which assumptions do you need for this? Is exactly the assumptions of Rolle's theorem. Okay, so you need that. Of course, what you need as well is that both functions are continuous, differentiable, and so on. Now, using Rolle's theorem, we can prove the mean value theorem. I first state the theorem. Okay, so again, we have a function. Assume that f satisfies. Now, first, f is continuous on AB. Second, f is differentiable on the open interval AB. So that's just the same as in Rolle's theorem. You do not have the third assumptions. The third assumption. Now, the mean value theorem tells you there exists a C in the open interval AB such that the derivative of f at C is equal to f of B minus f of A over B minus A. Okay, so maybe that's first, because this is maybe not so easy to understand, not so immediate to understand as Rolle's theorem. So maybe let's first look at some examples. Okay, so for instance, let's say our function is this one. Okay. Now, maybe it's good first to clarify what is this here. So you see that what we have here is exactly the slope of the secant, which passes through this point and this point here. So the slope here, so call it MAB of this secant, is exactly f of b minus f of a over b minus a. Okay, and what this theorem tells you is, okay, you can find the point C inside the interval AB such that the slope of the tangent is the same as the slope of the secant. Okay, so for instance, here you see, you just shift it up and you see, okay, that if you choose this C here, okay, then this C here will satisfy that the slope of the tangent at this point here is the same as the secant. And if you check more examples, okay, you will see that this is indeed always the case. Okay, now in mathematics we have a few theorems, okay, where if you see the theorem for the first time, you might not realize that this theorem is important. Okay, but this theorem will turn out to be the most important tool which we will learn which we have learned till now, and it will remain the most important tool now for a couple of weeks. So we will apply this theorem several times. This is one other difference to high school mathematics. I told you already one, or you should by now already have realized one big difference to high school mathematics, namely we try to more systematically build theorems. Like we have seen for limits, we first gave a definition of the limit, and then we started with some easy examples, some easy rules, and built more and more complicated examples. You saw the same approach for continuous functions and so on. So this is the first important new thing here at high school, at university level, namely we start from some definitions and systematically build more and more complicated theorems. And the other important thing you should learn is to recognize key ideas. And this is here a key idea. Okay, so this was the first. This was first proved by Lagrange. Okay, and the main contribution, because we will see next time that the proof of this result is pretty easy. Okay, not complicated. More or less follows directly from Euler's theorem by just defining a suitable function. So the proof is easy, but the main contribution of Lagrange was to recognize that this here is a key point, that this is an essential result on which we can build then and discuss many applications. So we will see that from this result, because roughly speaking, this result gives you a close connection between the function f and the derivative. Of course, the derivative, there is a connection because the derivative is defined as a limit of the original function. But if you just use the definition, it's not so easy to deduce properties of the original function from properties of the derivative. But we will see this theorem is the right tool in order to deduce properties of the original functions from the derivative. So for instance, if we wanna prove that what we have seen already several times and what you have used in high school, that if the derivative is larger than 0, this implies that the function is increasing. Okay, this is something you see roughly if you look at examples. If you want to prove this without referring to a picture, so without referring to a specific function, we will see this is the right tool here to prove this precisely, this statement. Okay, so are there any questions? So we will next time discuss the proof of this result, and then I will show you why this result is so important and why this result is one of the key results we are going to learn this semester.